All right, so briefly what I'm going to take you through is calculating occurrence rates, the particular research that I've been doing to measure the Kepler pipeline's completeness or detectability, what that means for the occurrence rates that we derive, like how much it changes the answer by. And finally, completeness is just one of these little bugs that you get that can change your answer. So I'm going to talk through some of the others. Mostly I'll be talking about completeness though. Okay, I won't go too much into what Kepler is. Courtney covered it yesterday. Kepler was a mission designed to measure the occurrence rate of planets like the Earth around stars like the Sun. So it's a satellite that looks at 100 square degrees, nearly 200,000 stars. It went for 4 years, so we have a lot of data. And just another plug, we have the Kepler light curves, the lists of candidates, and the pipeline products all available at the greatest collection of exoplanets the world has ever seen, the NASA Exoplanet Archive. You might have heard of it. Okay, so that was Kepler, launched 2009. Where are we at? Well, we're at the find all the planets stage. This was the press release that came out last week. There are now 5,000, nearly 5,000 candidates. The blue points are the ones that had been released in the previous catalogue 6 whole months ago. The yellow points are the new ones that were released last week. What we're really interested in, obviously, for Eta Earth is this kind of region down here. So this is 300 days, there's Earth. And you can see there's still not much there. But we're pushing down further and further all the time. You can see there's more yellow points there. So hooray, still finding more. I want to point out that this catalogue, the Completeness et al. Catalogue, was made with version 9.2 of the pipeline. And the reason that's important is because every time we make a new version of the pipeline, the sensitivity changes. So you need to be careful that you're using the detectability that we've measured with that version of the pipeline with the planets that we found with that version of the pipeline. Because especially the last 2 versions of the pipeline really changed the sensitivity at long periods. So it's a real gotcha. So don't take the 9.1 completeness and use it on the 9.2 catalogue and expect not to reduce your systematic errors. You'll just introduce a different systematic error. Okay, so again, I can kind of gloss over this a little bit because Courtney talked through it yesterday. But to calculate the occurrence rate of planets like the Earth, you need to know how many real Earth-like planets there were in your sample, which is really understanding the reliability of your catalogue. Like how many false positives did you have in there? How many things did you call planets that aren't really planets? They're binaries or they're just glitches in the data. Secondly, you need to know how many stars would you have found that planet around? And this is understanding the completeness. You want to understand the false negative rate. How many times should you have found a planet that you didn't find it? So you can find this limit between what's detectable and what's not. Now, the number of stars around which you can find this planet can be further busted out into stars around which that planet would have transited. So this is geometric probability that's come up a few times. And then this term here, for a given signal to noise, there's a probability that the pipeline would have found it. And this is the completeness that we're trying to measure with my research. So that's the geometric probability. That's the probability of it being detected for a given SNR. So the aim of my research over the last few years has been to characterize this, to measure this value for the Kepler pipeline. All right, so I know we have some visual learners amongst us, so here's another way of thinking about it. This is all of the events that create signals in the Kepler data. There are real planets, and then there are false positives. Some of those are astrophysical, some of them are just spurious noise in the data. Some fraction of these real planets will create signals that the pipeline finds. And some fraction of the false positives will also create signals that the pipeline finds. So these are all of the signals that the pipeline finds. Ideally, in a perfect world, all of the real planets that create signals would be found and labeled, and hooray, we found all our planets. However, some number of these creep in, and this slice of the pie is the reliability of the false positives. We need to know how big that slice of pie is before we can calculate the occurrence rate. And some of these real things get dropped. They don't get identified. So the slice of this pie, which is a different number, a different slice, also affects your answer. Now, I've suggested sizes here, but the point is going into this, we don't know how big these are. This could be like a quarter of the pie, and that would make a big difference to the answer. Okay, so far, there hadn't been a characterization of this probability, of the probability that a transit would be found by the Kepler pipeline given its signal to noise. But people have been doing occurrence rate papers for years. So what did they do? So a bunch of papers came out assuming that the pipeline worked as advertised, as if you had white noise and everything was hunky-dory and you found everything above 7.1 sigma. So that recovery rate looks like this. So I'll go into a little bit more what MES is later, but just think of it like a signal to noise. So a signal to noise of 7.1 is the pipeline's threshold. You need to be greater than 7.1. And that was chosen before launch to minimize the number of spurious things. But of course, as always, the data is noisier than you expect. So 7.1 turns out to have plenty of spurious things that happen. So what this is basically an error function, which has a center at 7.1 and a width of 1 sigma. It goes from 0, so we're not finding anything less than, say, 5 sigma. We're finding everything above, say, 9 sigma. And then there's this transition region in the middle. So this line here is 50%. So you would find 50% of the things at 7.1. And that just comes out of the fact that some of the things that you inject at 7.1, or some of the things that are really there at 7.1, are on noise that's positive instead of negative. So your transit's less deep than it should be, and then your signal to noise is less. So that's just a property of the fact that the data has noise in it, and you're not going to find everything at 7.1. Okay, so a bunch of papers came out just assuming that the pipeline had achieved its hypothetical theoretical maximum detectability. Now, a bunch of other papers came out that were like, well, you know, we don't think maybe the pipeline's doing that well, so what assumptions can we make? So a few papers came out. I don't know if Andrew's still in the audience, but Andrew's was one of them, Andrew Uden, that said, okay, let's be more conservative than that. Let's say that the pipeline found everything above 10 sigma and nothing below 10 sigma. And they chose little regions of parameter space that this was applicable in, but basically they were saying, okay, this is our detectability of the pipeline. It's a step function, everything above 10 sigma, we're complete. Other people chose different limits. So our paper came out by Dong and Xu, which chose the 8 sigma limit. They were a little bit more optimistic. They were like, I think it's complete above 8. So that's this part of the pie. And then finally, actually, Francois Frassine, what he did, his curve looks like this. It's a linear ramp between 6 and 16. What he did was model all of the false positives that should be in the Kepler data, just using a galactic Bayes-Sansone model. You know, the stars binaries should look like this. This is how many binaries we should have found in the Kepler data. This is how many we did find. Therefore, this is the detectability of the pipeline. Now, what I've shown with this 50% line, you can kind of rank them by how optimistic they are, by where they cross this 50% line. So the theoretical hypothetical maximum is the most optimistic. We'll find everything that we should find. And that's here. And then they become progressively more pessimistic until you get to Francois' quite pessimistic, you know, we're missing all of these things. So you take your detectability, and then you fold that forward in your occurrence rates, and I'll show that a bit more. But part of the problem was all of these different papers in slightly different parameter space using slightly different detectability assumptions came up with different answers. And then it's impossible to compare them, right? Like, if you get different occurrence rates, then is it because of this assumption that you made? Is it because of a different assumption that you made? So it was really hard to disentangle why groups were getting different occurrence rates. So clearly what we should do is measure this. We should actually find out what the detectability of the Kepler pipeline is. Now ideally, and what had been done previously for other studies, is that you would take your star and you would inject a whole suite of fake planets around it with different radii and different periods, and you would just try and recover all of them, and you would just map it out. So this is an example that Sarah Ballard and I did for GJ 436 with our EPOXI data. EPOXI was a spacecraft that did some observations of exoplanets many years ago now. You might not even have heard of it. But this is what we did for that, and you can see each line here is the detectability for a planet of a given radius out to a certain period. So for the 1 Earth radius planets, we did not have a lot of sensitivity. After 2 days, we had no sensitivity. We wouldn't have found them. But for planets with 2 Earth radii, actually, we were good out to 14 days. We were still finding 80% of them. So ideally, you would do this for every planet, for every star. And the problem is, as I mentioned before, Kepler looked at 200,000 stars. So this kind of really intensive, doing tens of thousands of injections into hundreds of thousands of stars, and also Kepler has a very long baseline, as I said, it observed for 4 years. It's just not computationally intensive. We already use the NASA supercomputer to do one run where we search for planets, let alone tens of thousands of runs. So we had to think about it a different way. And what we ended up doing was using the fact that we have 200,000 stars to say, okay, well, that's our Monte Carlo test. That right there. We have all of these statistical samples. So we'll inject one planet per star, and then we'll recover the average detectability. Now, I'm sure you can see the kinds of pitfalls that that comes into, right? Because what you're saying is the detectability is uniform across stars, which we know is not going to be true because the stars have different noise properties depending on whether they're dwarfs or giants, whether they're binaries or not. So you can already start to see that we're cutting some things here, we're letting things slip. But we're doing the best we can with the computing resources that we have. So this is what we do. We go and we inject one planet per star, and we run it through the pipeline as normal. So this is, I'm going to describe the results of our second transit experiment. The first one, which came out 2 years ago, basically looked at individual transit events to say, does the pipeline preserve the depth, the signal to noise of individual transit events? And it turns out that in the vast majority of cases it did. So that was great. That was going forward, that was a good confidence boost. So this is the second experiment. So what we did was take 1 year out of the 4 years of data, again, computing resources. We took 15 CCDs out of the 84, so we didn't do the full focal plane, we did about a sixth of a focal plane. For anyone who's played with Kepler data, these are the CCDs that I chose, and there's a lot of jargon here, but basically the idea was to sample a bunch of the different types of noise that Kepler has. There's changes in focus, there's electronic noise, there's the edge of the field, there's the center of the field. So we really tried to sample a bunch of these things to see if that would make any difference. Like, can you find planets more easily at the edge of the field than at the center of the field, depending on the focus? Now, again, so I remember I mentioned earlier that the catalog that just came out last week was a 9.2 catalog. This test was run with 9.1. And there was a big difference in the way the pipeline treated long period things between 9.1 and 9.2. So what I'm discussing here is relevant to the Mullally et al. Catalog that came out 6 months ago, not the Coughlin et al. Catalog that came out last week. It's just moving too fast, but we're trying to keep up. So again, just a gotcha going forward. So these are the injections. This is period here, the orbital period of the planet that I injected. This is radius, the radius of the planet that I injected. Across those 15 CCDs, we made 10,000 injections. And this is what we found. So we recovered 9,000 of them, which fantastic. But when you look at it, you start to see some things. For instance, this is period, so things below 1 day should typically have very high signal to noise. And we're missing a bunch of them. And then when you look out here at very long period, you start really realizing we're missing a bunch of them. But this out here, this is what we're looking at. This is what we're trying to determine. This was kind of a surprise when we first saw it. So this histogram is this plot collapsed in radius. So we're just looking at period now and the fraction of the injections that were covered as a function of period. So you can see between like 3 days and 30 days, we're up at 95%. So that's encouraging. But then you see this fall off that I mentioned. So this here, this short period fall off is due to the harmonic filter in the pipeline, which I'll talk about a bit more. And then the fall off at the other end is this signal to noise drop off that we're trying to map out. We're trying to work out when we go from detecting to non-detecting. Okay, so this harmonic filter. Before the pipeline tries to find transits in the data, it whitens the data. It uses a wavelet transform to turn the data ostensibly from red correlated noise into white noise. Then it applies the wavelet transform that it had applied to the data to the model of the transit so that you're fitting apples to apples. Now before it does that, before it tries to fit this wavelet filter, it tries to take out stellar variability. So a lot of these stars have some kind of action. There's spots, there's rotation modulation, there's other kinds of variability. So the pipeline tries to take that out. Now for very short period planets and eclipsing binaries, a significant fraction of the phase, the orbital phase, is spent in transit. And if you try and fit that with the Fourier series, you can. And it goes, hey, look, I found a variable signal, I'm going to take it out. Which is kind of a bummer if it's a planet. So here's an example of something that I injected. This is the light curve. This is 6 days worth of data. And here's one of my transits. Then here's another of my transits. And here's another of my transits. And this is what the harmonic filter tries to take out. I'm not quite sure what is happening here, why it's not grabbing this large stuff and it's kind of grabbing this little rumble. But you can see very clearly that it's like, hooray, I can totally fit this. I'm awesome. So it fits it, and this is what's left. So you can see my transit is, it's a bit misshapen there. then this one is just gone. And this one is bleh. So sure enough, when you try and find this planet, it's gone. It got fit out. So this really affects things less than 1 day, and does affect some things up to a period of 3 days. So what this means is it's really important for people to do independent searches of the Kepler data with their own pipelines. So I know Roberto Sanchez-Aweda did a short period search and came up with a bunch of things, which is great. But just to encourage you, there's no reason not to look for things in the Kepler data because Kepler's doing it. Because we had to make assumptions to do our data reduction to emphasize Earth-like planets in long periods. So the short period stuff we don't care as much about, so we'd rather lose short period things and keep our ability to find long period things by removing stellar variability than turn this off. We tried turning this off and then everything had planets everywhere, which was obviously not true. So go look in the Kepler data. So the harmonic filter it removes planets altogether, but it also has another effect, which is that it reduces the depth of transit. So that first transit that I showed that started out deep and then was half the depth, that's another important thing for completeness, because you're going to, the catalogue of planets that you get out of this is going to be systematically offset in radius at these short periods, because we've reduced the depth of all of these things. Well, not all of them, but a large enough factor that I would be worried. So this is the ratio of the final depth that got fitted out at the end of the pipeline versus the injected depth. So 1 means that we've recovered it at the right depth. This is period here. And so you can see, again, like for these short period things, so this is like 3 days. For things below 3 days, there's this large population of things where the depth was really changed. So it's another thing you need to kind of fold forward when you're thinking about occurrence rates. So another thing I want to point out, another way that transits can be distorted or dropped, is that the pipeline treats the edges of data differently. So the edges in time, I mean, there are gaps every month when we download data. Then there are gaps when the spacecraft is having a nap. And the gaps near those data often have large systematics because of the temperature changes that happen when the spacecraft is either turning to download data or mostly turning to download data. And so in order for those large systematics to not just trigger the transit search every single time you run it on every single gap, we de-weight those cadences. So we say that they don't count as much towards your total signal to noise. We also try to correct them to preserve any transit that's really there, but that correction can also distort transits that are there. So here's a light curve where I've injected, now this is time, where I've injected this transiting planet. So blue is what I injected, and red was what was recovered at the end of the pipeline. You can see for this one, for this transit here, something's gone wrong. We didn't recover that transit as well as we thought. And if you zoom in, the red points, you can see they're about half the depth of this. And this is this correction that I was talking about. Near gaps, we try to correct the data back to the baseline. And if there's a real transit there, that means the transit gets corrected back to the baseline, and you're going to reduce your depth. So I should say this is a really small number of just pathological cases. And in general, we're doing a very good job of preserving the transit depth. This is back to this first experiment that I was talking about. So I'm just describing some of the tiny ways in which the pipeline can affect things. Okay, moving forward. This is this MES that I was talking about before. So the pipeline, the Kepler pipeline, you'll see this a bunch, so I want to make sure you understand what it is. So the MES is the multiple event statistic, and that's basically the signal to noise of our transit. What it really is the signal to noise of that whitened transit model that I described compared to the whitened noise. So if you're looking at the original Kepler data that hasn't been whitened by the waveform, you're not going to recover this MES number the same way. So the MES, so it's a signal to noise in this whitened domain. And Courtney talked through this yesterday, but I'll just reiterate. You can calculate it by the observing baseline, so Kepler's 4 years. This is basically the duty cycle of your observations, like what fraction of the time you're actually on the target. So this number is typically 85 to 90% for the Kepler targets. P is the period of your planet that you injected. Delta is the depth, the transit depth. CDPP is the Kepler's measure of the noise in a light curve. So just think of this like the RMS in the light curve. And you can see that these two terms basically reduce down to the square root of the number of transits times the signal to noise in a single transit, which is basically what you expect. But I just wanted to break it out for you because you'll see it in Kepler papers and I feel like people don't understand what it is. So So that's the ground truth. That's what the universe gives us. The universe gives us a planet of this size, which corresponds to that depth and that period, and this is your MES. However, the signal to noise that actually gets into your light curve is modified slightly by various things, including the fact that your aperture could be diluted. You could have other stars in the aperture, which means your depth is different. So this number is not what you expect it to be. As I mentioned, there are processes in the pipeline that de-weight things. They take out cadences, which really reduces this number, reduces F, so you actually find fewer transits than you expect. And even things like the shape of the model template. In 9.1, we fit a box shape, but in 9.2, we fit a transit shape. And that's going to change, basically it changes your average depth of what you're fitting, so it's another depth effect. So these are all subtleties that have to be included. So again, I'm sorry, I'm talking you through the real nitty-gritty sausage-making stuff here, but it's all really important. So for this population that I injected, this is the period here, and this is the radius again. So the same plot as before, but now I've plotted this expected MES number as in the color here. So you can see what you expect, that the low period, high radius things have very high signal to noise. They're the easiest to find. And the long period, small things are the hardest to find. So this is this exact trend that we're looking for, and we're trying to map out where the pipeline stops doing as well as we think it should. Okay, so let's turn this into this. So this is the expected MES, as I've just described. So here's 7.1. And this is the fraction of the things that I injected that were recovered. So what we were expecting for the hypothetical best performance of the pipeline, which is this red curve, was that at 7.1, you'd have 50% recovered. And you can see we're down at like 20%. So we're not doing as well as we hypothetically could if everything worked perfectly, which is fine. It's not that, the point is not how close we get. The point is that we know the answer so that we can use it in our calculations. And you can see that we're also not doing as poorly as we could have. And I should point out here that Francois' ramp that he derived was actually a different version of the pipeline and one of the earlier ones. So it's possible that the pipeline improved significantly since then, and actually hopeful that the pipeline improved significantly since then. So this green curve here is a fit. It's a gamma cumulative distribution function fit to the distribution. And this represents, for the FGK dwarfs, how the pipeline's doing. Now, the reason I've cut it down into FGK dwarfs is, one, that's what Kepler is designed to care about more. And two, we feel like we understand the noise properties of these stars a little bit better. If I look at the rest of the targets, so that's M dwarfs or giants, I get a lower detection sensitivity. So if I just flip back and forth between these two. So that's the FGK dwarf, so that's things between 4,000 and 7,000 Kelvin and things with a surface gravity of greater than 10,000 grams per second squared. And then this is the rest. This is the giants and the M dwarfs. Now both of giants and M dwarfs have more correlated noise in their light curves than just the FGK main sequence stars. So to reiterate, this is not to say that they've got a greater RMS. They do, but that shouldn't hurt us. It should just mean that we find bigger things around them. What I'm saying is that they have more correlated noise, so more noise point to point. The point-to-point noise is more predictable, is what I'm trying to say. And what that means is when you're looking for transits, it's easy for the real transits to be masked by features in the data that are correlated and look like transits. So this is just to show the noise properties of the stars. So this is basically a poor man's HR diagram. This is temperature going backwards here and the surface gravity here. So this selection that I did, the FGK, is like 4,000 to 7,000 greater than 4. So it's this wedge here. So what I'm leaving off is the M dwarfs and the giants, and whatever these are. I'm not a stellar person, but I'm concentrating on these. And these are the ones that have both increased CDPP, so this color here is the noise. So they have increased CDPP, but they also have this increased correlated noise, which is harder to find things around them. It's easier to find small things because the stars are small, but it's harder because they're noisier in a way that we don't like. I know, work that out. All right, so what does it mean for current state calculations? So let's go back to the catalog that Mullally et al. Put out at the start of the year. So this is the 9.1 catalog. And let's just concentrate on this box down here. This is 50 to 200 days from 1 to 2 Earth radii. And this result that I'm going to be talking through is a paper that Chris Burke and I and the rest of the team have submitted, I've changed it on the other slide, but I didn't change it here. It's submitted, it's available in the archive, so you can go find this. But I'm just going to talk through it here. So we take this box. Now the way we calculate our occurrence rate, if I had another 40 minutes, I'd tell you all of the different ways there are of calculating occurrence rates and the pros and cons of each. There's really two major schools and a bunch of minor schools of thought. One is that you calculate for each value of period and radius what the occurrence rate is in that box, and then you have a histogram. And the other is that you fit a function across that space. You say, okay, I think that there's some physical law underpinning the distribution that I can fit, and instead of like dividing it up into boxes and calculating the occurrence rate for each box, you actually try to fit you fit a function across the parameter space you care about. So that's the one we're using here. So we're trying to fit a function across this box. It's 5 to 200 days, 1 to 2 Earth radius planets, using the Q1 to Q16 catalog. Okay, so using the detection efficiency that I calculated with my injections, this is the occurrence rate we get of planets from 1 to 2 Earth radii, 50 to 200 days around G and K stars. We've cut it down a little bit here to try and match up with other people's samples better. So we dropped the F stars at this point. We're just doing G and Ks. So this is our occurrence rate. So it's about 33%. 33% of stars have a planet in this radius. So that's great, but what does it mean that we chose my measured detection efficiency compared to some of the other assumptions in the literature? Okay, so this is the difference that you get in the derived occurrence rate. If you choose the most optimistic, if you said that the pipeline found everything that it should, you were going to go with that, this is what you would have derived. So more like 25%. And so the optimistic occurrence rate is less because you think you found everything there was to find. So there are really 3 planets in this box, therefore the occurrence rate is this. The pessimistic occurrence rate is higher because you think you missed half the planets in the box. So there's really 6 planets in this box, therefore the occurrence rate is higher. So just to make sure you're thinking about it the right way. So the differences are significant. The difference between the baseline measured occurrence rate and if you had chosen the pessimistic detection efficiency is 3 sigma. I mean, that's a different answer. And then it's 2.5 sigma between that and the optimistic occurrence rate. So that's really interesting. So, I mean, these are the sorts of differences we see in the literature and the occurrence rates that come out. I'm going to show on the next plot some of the comparisons. But maybe this can go some of the way to explaining the tension between the different groups' results. But it's only one aspect. So I've spent a lot of time talking about completeness, but we also investigated a bunch of other things. So here is a bunch of other systematics that can also change your answer. So let's talk through them. This is the black curve here with the black triangles. So in our occurrence rate calculations, we assumed that everything had an eccentricity of 0. It's all in circular orbits. And we know that's not true. Radial velocity surveys have told us that, above 10 or so days, there's a distribution in eccentricities. Now, eccentricity, by assuming it's circular, it gives you a certain duration of the transit, which gives you a certain signal to noise of the transit. Now, if everything has a different eccentricity, if everything has a higher eccentricity, then that duration will, on average, be longer, which will give you a different signal to noise. And what that ends up doing is changing your occurrence rate because you've changed this duration systematically for all of your things. So what we did was, okay, let's assume everything has an average eccentricity of 0.4. And what does that change? How much does that change our answer? So by changing the eccentricity of all of our planets from 0 to 0.4, we've shifted it. We've shifted it towards a lower rate. Another effect is the stellar properties. So we've talked a lot about the fact if you don't know the star very well, then you don't know the planet very well. What we used for the baseline calculation was the Huber et al. Catalog that the stellar properties working group working for Kepler came up with. But if you had instead used the original Kick values, that was the Brown et al. Catalog that came out before launch, you would have found this as your occurrence rate. And that's because the stellar radii in the original Kick catalog are systematically different from what we think the real stellar radii are. Another effect here, so these 2 blue lines, there's the one without the points and there's one with the points in here, you can just kind of see it, is the reliability of the candidates. So remember I said earlier, there's those 2 pieces of the pie. There's one piece which is calling things planets that aren't planets, and there's one piece which is not calling things planets that are planets. So I haven't talked anything more about that, but it's an important systematic, and people are working on measuring how reliable the Kepler planet candidates are. So here what we've done is said, okay, let's say that compared to our baseline, here we go, compared to our baseline measurement, we're going to include candidates that we might not have otherwise included. We're going to be more generous. We're going to take some of the scrappy candidates on the edge that you might not spend your 8-meter Keck time on, but still might be planets. So we're going to include a bunch of these things. So if you increase that number of planets, you get a higher occurrence rate. Whereas if you raise the bar, if you say, okay, I really need to only look at things that are definitely planets, I'm going to eliminate all of these scrappy things, you get a lower occurrence rate, which is here. So even just choosing your bar for what you call a planet candidate out of this catalog changes your answer. Finally, a last one that I wanted to talk through is we wanted to do this comparison to other surveys. And some of the other surveys, including Eric, I'm not sure if he's here, but Eric's survey, Eric Pettigrew, he just found the first planet in each system, which is typically the highest signal to noise planet. So if you just take the first planet, then you've got fewer number of planets, and therefore you've got a lower occurrence rate. So that's this line here. Okay. But what I'm trying to say is, check this out. These are all of the different answers you get with the same Kepler data, just changing your assumptions. And that goes from like 0.15 to 0.7 planets per star in this bin. So we don't really know the answer yet. But we're finding out all of the things we need to know the answer. So how does it compare to the literature values that I talked about before? So again, this is our baseline. This is Eric's model here, the black line. This is Heismelder's, who did another analysis. And this is, again, our first planet only. Wait, this is our first planet only, and this is our combined. If you take these four, 1, 2, 3, 4. If you take these 4 systematics, if you just talk about those ones, then we can match Eric's result. But we don't believe that we should use those 4. But it's possible to reproduce Eric's result if we make those assumptions, and presumably in line with a lot of his assumptions, including finding only the first planet. So I just want to talk for 1 minute about the fact that completeness doesn't end at the end of the pipeline. So the pipeline produces a set of candidates. And then we have to vet them. We have to decide, is this a good candidate or is it not a good candidate? Now, up until the Coughlin et al. Catalog, this was done by people. And I was really horrified about having to test this, like with my injections. I was like, this is going to be a nightmare. I don't want to do this at all. So luckily for me, they have changed recently to doing the vetting automatically. So there's 2 different methods that they've come up with to kind of automatically classify these candidates into whether they're planet candidates or false positives. One of them, if you saw the pop yesterday by Joe Catanzarite, who's here, he has a poster outside. One of them is a machine learning algorithm, which basically looks at all of the things we've ever called planet candidates and then looks at all the light curves and says, okay, well, I think these are planet candidates and I think they're not. The other one is like a rule-based method where the humans were making decisions. It has a secondary eclipse of great significance. There's a centroid offset. There are all of these decisions that get made. So this rule-based one just says, okay, I'm going to do that automatically. If the secondary eclipse is greater than 3 sigma, you're out. You're not a planet. So it just uses the same rules that had been used previously, but automatically applied. Now the best thing about this is that I can take my transit injection and just push it straight through, and we can find out how well they do. Do they classify all of my real injected planets as planets? And this is the first time we've been able to classify that part of the pipeline, or that part of the process, since it's not part of the pipeline. So coming soon to an archive near you is my latest, greatest, my 3rd transit injection experiment, which is now, finally, it's a full 4-year, it's all of the observations. It's all of the CCDs, so it's all of the targets. I'm extending the parameter space, so it's going to be out to 500 days. So remember, previously I only went out to 200 because I needed 1 year. So now I can talk about the completeness of things in the habitable zone, the things that we really care about. So here's just a teaser of the results. I'm not going to tell you anything about what these populations are or what these numbers are. I'm just going to say this is exciting and interesting things are coming out. And the full table of what I injected and what we recovered is going to be available at the archive in the next few months. So if you're interested in occurrence rates, this is where I would start. Thanks very much.
In the new release, I noticed there's quite a few new candidates that have excellent candidates. Those should have been discovered very easily from the first readings. Why are they still popping up?
So the question is, why are we still finding short period, large radius objects in the catalogue? There's a few different factors. One of them is objects were still being added to the observing list towards the end. So some of these are things that only had a few months of observations towards the end of the project, and they didn't get 4 years. Some of them are things where the original versions of the pipeline basically searched until they found one planet, then classified that planet into a false positive or a planet candidate, and then if it was a planet candidate, it kept going and looking for more planet candidates. But if it was a false positive, it stopped. So you could have real planets in those systems that didn't get searched for because the highest signal to noise thing was a false positive. So that was an important aspect of completeness, that the pipeline didn't keep searching these objects where if it found a high signal to noise false positive, it was like, okay, I'm done with this light curve, I'm moving on. So you could find planets in those that were real that just hadn't been found by the pipeline. So we've changed that in the last couple of versions of the pipeline. Now we just keep iterating down to where we're not finding anything, and then classifying whether it's a false positive or a planet candidate. Some of these things might be things that the harmonic filter ate, but actually, in general, the really deep things, if they were observed early enough in the mission, we did enough by eye looking that most of those should have popped out. So I'd be surprised if the harmonic filter was finding those, was spitting those things out now. But that's some of the reasons why. It's true, there has been some, oh sorry, so the comment is the harmonic filter is one of the parts of the pipeline that can change from version to version. Possibly it's just changed its behavior. I know that they tried turning it off, and that was bad. I don't know that they played with it too much, but they could have. So the comment is because we're injecting planets randomly across the stellar sample, we might be biasing ourselves against populations of particular types of planets around particular types of stars. I would hope that we would mostly wash that out because we've busted it down into a signal to noise measurement. So the small stars around the small planets should have a signal to noise that we then measure. So the signal to noise, by characterizing it as signal to noise instead of for each star, what you really want is a contour map of the completeness with radius versus period, and that would tell you all the information you needed. But we can't do that on a per star basis. So instead, we characterize that radius and that period around that star as a signal to noise measurement. And then we say, for signals that have 7.1 sigma, this is how many times we'd find them. This is what a fraction of the time we'd find them. So I'm hoping that that would kind of fix that problem. So I know Jason Rowe has looked a lot at measuring the dilution. So what the pipeline, so the question is, can we look at the dilution and see if there's any correlation with stellar parameters? We make a guess at how diluted our planets are because we've done a map, basically, of where all the stars are and how much of their flux contributes to our aperture. So we try to correct that, but we know that that's wrong. It's an approximation. And I know Jason Rowe has done a lot of work looking at the distribution of dilution. I'm not sure if he's broken it out by stellar properties, but I think he would have the answer to that. I certainly haven't done anything with that. In my simulation, I just assume that the dilution is correct and go from there, but it's definitely another source of error. I would hope that that one's more. Oh, the depth? The depth change. Okay, that's fine. Sorry, I was thinking about it in terms of aperture dilution. Right, so the question is, the depth change that the pipeline gets at short period, does that correlate with different stellar parameters? I haven't looked at that actually, but that's an interesting question. It's almost certainly the case that it depends more on the period that you've put in. But the characteristic timescales of the noise from the star and the period of the thing, the confluence between those two is where you get into trouble. So I bet it does have something to do with stellar parameters because it's the timescale of the correlated noise.